Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden world that organizes every single file on your computer, from your family photos to the operating system itself. We're talking about the unsung hero of computing, the file system. So, the digital mass. To really get why file systems are so critical, I want you to imagine a massive library, but instead of neat shelves, every single book is just thrown into one giant, chaotic pile on the floor. That's exactly what a storage drive, whether it's a hard disk or an SSD, looks like without a file system. It's just a raw, completely jumbled mess of data.
And this is where the file system steps in. It's the essential librarian for your computer. It's the software that takes that absolute digital chaos and transforms it into an orderly, accessible system that we can actually use. It is literally the difference between a junk pile and a functional library.
Okay, order from chaos, files and directories. So how does our librarian, the operating system, actually create this order? Well, it all starts with two fundamental building blocks that you use every single day, probably without even thinking about them: files and directories. The first and most basic piece of the puzzle is the file. Now, the key concept here is abstraction. A file isn't just a physical chunk of data. It's an idea the OS creates. It groups related information from those raw disk blocks and presents it as one single thing. It's kind of like binding a bunch of loose pages into a book, giving it a name and a clear beginning and end. Right, and if our files are the books, then directories, well, they're the bookshelves. They're the containers that group related files together, creating that familiar tree structure of folders inside of other folders. This is what lets us organize everything logically and find any specific file using its path.
All right, moving on to the librarian's index card, talking metadata and inodes. So we've got our books on the shelves, but how does the system know who wrote the book, how big it is, or who's even allowed to read it? For that, it needs a cataloging system.
And this brings us to a super important term, the inode, which stands for index node. You can think of it as, literally, the librarian's index card for every single file. It's a small but incredibly powerful data structure that stores all the critical information, the metadata, about a file. So what's actually on this index card? You can see it for yourself. Anytime you run a command like ls-l in a terminal, you're essentially reading that file's inode. All this info you see, the permissions, the owner, the size, the last time it was modified, all of it is stored in the inode. But here's a fun little detail. Notice the one thing that isn't in the inode? The file name. That's actually stored in the directory, which then points to the correct inode. So with all our files cataloged, the file system now faces two big real-world challenges. Let's talk about placing and finding data. First, where on the actual disk should it place the file's data? And second, how can it get that data back as quickly as possible? So that first challenge is called allocation. The simplest method is contiguous allocation, where a file's data is just stored in one big, continuous chunk. It's super fast to read, but if you need to make the file bigger later, well, you might run out of room. The alternative is linked allocation. Here, the file's blocks can be scattered all over the disk, and they're just linked together, kind of like a scavenger hunt. It's way more flexible, but as you might guess, it can be slow. And that whole scavenger hunt approach leads directly to a classic problem called fragmentation. When a file's data blocks are scattered all over the place, the physical read head on a hard drive has to jump around constantly just to piece it all together. This is super inefficient, and it slows everything way, way down. Which brings us to the big performance problem. On a traditional spinning hard drive, you've got that physical read/write head that has to literally move across the platter to find data. So if it's handling thousands of requests at once or trying to read a fragmented file, how does the OS stop it from just frantically jumping all over the place? The answer is pretty clever: disk scheduling algorithms. The simple way is first come, first served, but that's really inefficient. A much smarter approach is the scan algorithm, and it works just like an elevator. The read head sweeps back and forth across the disk, servicing all the requests in its path, just like an elevator stopping at floors on its way up and then again on its way down. And the performance difference here is absolutely staggering. Just look at this chart showing the total head movement. By simply being smarter about the order in which it handles requests, an algorithm like Scan can dramatically reduce the physical work the disk has to do. And that means a much faster and more responsive system for you. Okay, enough theory. Let's make this real. We can actually see these concepts in action with a few simple commands. This is how we speak the language of the file system. First, let's create an empty file with the touch command. When we do this, the file system allocates a brand new inode, our index card, and then it creates a directory entry that links the name myfile.txt to that inode. Now, we'll use ls-l to see its metadata. And there it is. That output shows us the permissions, the owner, the size, all the information from that file's index card, its inode, that we were just talking about.
We can even modify that metadata directly. Using the chmod command changes the file's permissions. What's cool is, when we do this, we're not touching the file's data at all. We are reaching right into the file's inode and changing who has the right to read, write, and execute it. Of course, all these files live on a storage device that the OS knows about because it's been attached to the system using the mount command. And if we wanted to see how much space is being used on all our mounted file systems, we could use the df command, which just stands for disk-free.
So you can see, file systems are so much more than just folders on a screen. They are this complex, elegant, and absolutely essential layer of the operating system. They provide the structure, the performance, and the integrity for every single piece of data in our digital lives. So we've seen how our data is organized and how the system finds it efficiently. But just organizing our data isn't enough, is it? How do we keep it safe and secure? How do we control who can access what? Well, that sounds like a story for another explanation. Thanks for joining us.